So what is the role of the models and what is the purpose of the models? We will learn as we go along, but we already mentioned several times. I said we will not distinguish between climate models and system models for now, but we should say something about weather models and climate models. Weather models typically are integrating for just a few days. We will see why that is when we come to the history of weather and climate models later in this same chapter. But basically weather models are trying to predict the weather typically at local scales from now to next few hours and next few days. Turns out that actually weather cannot be predicted beyond about 5 to 7 days. Maybe there is predictability out to 10 days. Predictability means there are processes in the system which have memory of some sort which we can use to say what will happen in 10 days. For example, the large-scale systems which bring weather like high pressure and sunny weather, or low pressure and rainy weather over mid-latitudes, the US and let's say Europe, they tend to linger around for 10 days, so they can give you predictability for 10 days, whereas beyond that there are issues of chaos that we will talk about a little bit later. So weather models then are integrating for a short time scale, and they have to be reliable at local scales. So they tend to be very high resolution, which means they have many more boxes in representing the sphere, or they can be representing just a region. So we'll talk about global models and regional models as we go forward. Which also means remembering that computational requirements depend on how many grid boxes we use to represent the sphere. Weather models can have high resolution. Let's look at the numbers later on. Also, it turns out that weather for the next few days doesn't depend so much on what the ocean is doing, because ocean has a high heat capacity. It warms slowly and cools slowly. So think of a pot on a stove, and you turn on the fire, the heat, the pot, which is made of typically metal, will heat up very fast because it has a low heat capacity. The liquid or water, milk, whatever inside will warm up slowly. And when you turn off the fire, the pot will cool faster than the liquid inside. The same happens with the ocean. So on a day-to-day time scale, the ocean doesn't change rapidly. So weather models typically just assume the ocean is remaining, let's say, at the same temperature at each point, not the same temperature everywhere. So it'll be warmer in the tropics and colder in the high latitudes, but it will remain so for the next few days when we are making the weather prediction. The atmosphere has low heat capacity and can move fast. Land also can cool and warm fast. So those are represented actively, which means they are changing as the integration is happening, as opposed to the ocean, which is fixed. So that's the weather model. Under climate model, the ocean varying slowly does become important even at the time scales of seasons or even weeks. So that's the difference between climate and weather models. So the purpose of climate models, then coming back to our main intent of this introduction to climate modeling, is often actually predicting specific climate events that we will see examples of, or could be understanding the process of, let's say, the monsoon, or could be some other phenomenon like the El Nino and so on. So what do they have to do? They have to obviously balance the energy to start with. So we know there is shortwave energy coming from the sun, about 341 watts per meter squared, changes a little. About 30% of it is reflected right away. In total, 30% is reflected, so 100 watts per meter squared is reflected back to space, some of it from the atmosphere itself and some of it from the surface. You can see that a lot of the energy that remains makes it to the surface, which is used to heat, to evaporate, to do many processes on the surface, and so surface then emits energy at thermal band, infrared energy that we talked about before. So you can see that the energy that is brought in is bounced around from the surface to the atmosphere, back to the surface. So you get numbers here that are much bigger than the energy that we are actually receiving, because it's like a blanket. If you stay in the blanket to get warm, you're trapping your own body's heat to create energy that keeps you warm. Right? It's not an electric blanket, it's just trapping your own heat. So similar things happen here, and essentially what has to happen is the net incoming solar radiation has to be balanced by net outgoing long wave radiation. So 341 minus 102 is 239, so 239 is going out with lots of processes in the middle, like greenhouse gases, the clouds, all the other processes that we talked about before, aerosols, chemistry, vegetation, evaporation, precipitation, winds, etc., etc. That's what the models have to do, right? And because we are on a sphere, we also end up receiving more energy than being lost to space in the low latitudes, and receiving less energy than being lost to space at high latitudes, which we did in the energy balance chapter before. This means energy is constantly being moved from low latitudes to high latitudes, because you don't want the tropics to get warmer and warmer, and they don't, and you don't want the poles to get colder and colder, and they don't, which means energy is being moved, and that energy is being moved by winds, ocean currents, evaporation, energy being picked up, precipitation, energy being released, and so on and so forth. This is what the climate models are doing. What is the role of the climate models? This is kind of a schematic that Tom Stoker provides here. Role of climate modeling in climate science. So climate and environment. So we have climate and environmental parameters like temperature, humidity, rainfall, whatever else you can, winds, all right. So there are transfer functions, which means there are ways in which they are measured and stored in climate and environmental archives. So there are measurement techniques involved there, and you create climate and environmental data. So you can have many observations of temperature, winds, ocean temperatures, ocean currents, humidity, clouds, aerosols, chemicals, and so on. And then at the other end you have numerical models, which is what we are focusing on, which have so-called governing equations which solve for balance of momentum, mass, thermodynamics, mass, so continuity, energy, so things that should be conserved like mass and energy, momentum, and so on. So we code them up, we solve them, so we have process studies that will give us model output, what are called model data, which the purists will not be happy if you call the model output as data. Data, they say, is what you measure directly, but there are details we will not worry about. So there are ways in which we can combine data and model output to synthesize and produce information, either for process studies, for predictions, for making decisions about the future, and so on and so forth, right? Or understanding the past climates. Why did ice ages happen? How much did CO2 change during an ice age to a end of the ice age, and so on and so forth. So that is the role of climate modeling. There are always models that are designed specifically for some purposes. So for example, here we are looking at reconstructed annual temperatures in the northern hemisphere over the last 1200 years from different people. So different evidences from tree rings, from ice cores, from historic records, from lakes, ocean sediments, corals, and so on are used by different people, and usually you don't measure absolute temperature, you measure deviations from a baseline. So here we are using baseline of 1961 to 1990. So this shows that except for a couple of products here which show a little bit of warming or warmer temperatures here in the medieval warm period, then we had the little ice age, so it was cooler than the modern period. And then the main point of all these products is that the temperatures have accelerated above the base period, and this is what we call global warming. So the instrumental record here is relatively short, so when you go back in time you have to use other proxies, what we called paleo proxies before, to reconstruct past temperatures, and there are deviations from each other, so the range of uncertainty is large because you are typically using corals in one location and trying to combine multiple corals to estimate global temperatures. These are global temperature deviations, so there is always going to be issues in terms of gaps in space, gaps in time, and so on. But models can then see whether they can reproduce this because if they are good models, then knowing the change in solar forcing which was involved in the little ice age, land use change because we deforested, volcanic eruptions, greenhouse gas changes, and so on, models should be able to reproduce past climate variability, otherwise we cannot trust them for the future either. Right? So that's the goal of modeling in that case. So changes in global mean temperature since 1860 in here, and heat uptake in the ocean since 1955. We don't have good data for ocean uptake before. So gray bands for observations and the lines for different model runs. So you can see that the comparison between the range of estimates from observations and models is remarkably good. There are some mismatches, but you can see that there are uncertainties here which were actually corrected because it turned out that there were some problems in the way either data were documented or they were calibrated and validated and so on and so forth. So when you go data can have problems, especially when you go back in the past and systems change. Before, the ship would drop a bucket, take the water on board and measure temperature, for example. That would result in loss of heat along the way and so on, whereas now you can drop instruments into the water and measure temperatures directly, which are going to be much more accurate. So you can see that the range of observational estimates become narrower as you come into the current period, because now we have more observations and more calibrated, validated observations, whereas the uncertainty in the ocean uptake still remains relatively large compared to temperature, but it was larger in the past as well. Okay, so let me stop that here and come back and talk a little bit about the history of evolution of models and the key players that were responsible for bringing us progress along the way. And that should conclude this chapter with some examples of climate models and climate predictions and the use of climate models for various purposes. Okay.